In the last lecture, we introduced the notions of Hermitian matrix, unitary matrix, and of real orthogonal matrices. These were the three important notions that we introduced. Let us recollect. Suppose A is an n by n complex matrix, we define A star, the Hermitian conjugates, as the transpose conjugate. So, you flip the matrix and conjugate every entry, you get the Hermitian conjugate A star. Then we say U belonging to C n n is a unitary matrix if U star U is the identity matrix, and hence U star will also be identity. This means U star is U inverse and U star inverse is U. Then we say the matrix is unitary. Now, suppose U is unitary and its columns are phi 1, phi 2, phi n, then we have U star U star will be the columns flipped and conjugated, and U will be phi 1, phi 2, phi n. When we multiply these two, we get a matrix, let us say K J, let us use K J R, a matrix K J R, 1 less than or equal to j less than or equal to n, 1 less than or equal to r less than or equal to n, where K J R is simply phi j star phi r. Now, since U is unitary, U star U must be identity, but if U is unitary, U star U must be identity. Hence, K J R must be equal to 1 if j equal to r and 0 if j is not equal to r. Because for an identity matrix, the diagonal entries are all 1 and the off diagonal entries are 0. Comparing with this, we get phi j star phi r is equal to 1 if j equal to r, 0 if j is not equal to r. This says the inner product of phi r and phi j is 0 if j equal to r, 1 j not equal to r, and 1 if j equal to r. That says the phi 1, phi 2, phi n are orthonormal vectors. Thus, we see that U is unitary, then the columns of U form an orthonormal vector. So, what is the conclusion? The conclusion is U is a unitary matrix imply the columns of U form an orthonormal set. Now, we have verified last time that if the columns of U are orthonormal, then the U is unitary. So, we had seen that columns of U are unitary or orthonormal implies U is unitary. Thus, combining these two, we get the important conclusion that U is unitary if and only if the columns of U form an orthonormal set. Thus, we can easily recognize whether a matrix U is unitary or not by looking at its columns and seeing whether they form an orthonormal set. So, let us look at some examples before we see the real version. Let us take the matrix U to be 1 I 1. Then the columns are 1 I and I 1. If you look at their dot product, so we have the dot product of 1 with 1 I with I 1. So, the first component into the conjugate of this first component of the second vector plus second component of the first vector times the conjugate, and that is equal to 0. So, the column phi 1, this is the column phi 2. So, we have phi 1 comma phi 2 is equal to 0. So, the columns are orthogonal, the columns are orthogonal, but their lengths, the length of phi 1 squared, that is phi 1 comma phi 1 is 2, not equal to 1. Similarly, phi 2 squared, which is phi 2 comma phi 2 is equal to 2, not equal to 1. Therefore, even though the columns are orthogonal, they are not of length 1, and hence U is not unitary. Let us look at another example. U equal to 1 by root 2, I by root 2, I by root 2, 1 by root 2. Now, we have the columns are phi 1 equal to 1 by root 2 and I by root 2, and phi 2 equal to 1 by root 2, I by root 2, 1 by root 2. Again, if we take the inner product of phi 1 and phi 2, we get the first component of phi 1 into the conjugate of the first component of the second vector plus the second component of the first vector into the conjugate of the second component, which is 0, and hence the vectors are orthogonal. So, phi 1, phi 2 are orthogonal. Also, phi 1 comma phi 1 is 1 by 2 plus 1 by 2. The inner product of phi 1 with itself is 1 by 2 plus 1 by 2 is 1. Phi 2 comma phi 2 is also 1 by 2 plus 1 by 2, which is 1, and therefore, they are normalized. Hence, phi 1, phi 2 form an orthonormal set. So, thus the columns of this given matrix form an orthonormal set, and we observed then it must be unitary. So, therefore, U is unitary. We can directly check this fact by calculating U star U. What is U? It is 1 by root 2, I by root 2, I by root 2, 1 by root 2. So, U star will be 1 by root 2 minus I by root 2 minus I by root 2 1 by root 2. It is transpose and then conjugate times U will be 1 by root 2 I by root 2 I by root 2 1 by root 2. If we take the product, I get 1 by 2 minus I squared by 2, which is plus 1 by 2, which is 1, and then 1 by I by root 2 minus I by root 2 minus I by root 2 plus I by root 2, again we get 1, which is I 2. So, therefore, we directly verify that U star U is identity. So, if the columns are orthogonal, it is not enough. If the columns are normalized alone, it is not enough. If the columns are orthonormal, then the matrix becomes unitary. In the real case, in the case of real matrices, we say O belonging to R n cross n is an orthogonal matrix if O transpose O is identity. In this case, the columns will be orthogonal, orthonormal, but with the real inner product, because we are now everything is real. So, we let the real inner product in R. As an example, look at the matrix U equal to 1, 2, 2, 1. We have U transpose is equal to U, but the columns are not orthogonal and not of length 1, and therefore, U is not orthogonal, is not a orthogonal matrix. On the other hand, if you look at the matrix U, which is 1 over root 2, 1 over root 2, 1 over root 2 minus 1 over root 2, we see that the columns are orthogonal and have length 1, and therefore, columns form orthonormal set. Columns form an orthonormal set, and hence U is an orthogonal matrix. So, these were two important notions that we introduced last time, namely the unitary matrix and the orthogonal matrix. And the most important class of matrices that we introduced was Hn, the class of all Hermitian matrices. Hn is the collection of all those complex matrices for which A star is equal to A. That is, they are self conjugate, they are Hermitian conjugate it itself. We observed the following important properties. Following important properties of any matrix in Hn. That is, any Hermitian matrix will have these following properties. The first property we had was that A belongs to Hn, that is, A is a Hermitian matrix, implies Ax comma y is equal to x comma Ay for every xy in Cn. Then we observe that all diagonal entries, A belongs to Hn, implies all diagonal entries of A must be real. We also had observed that if A belongs to Hn, that if A is a Hermitian matrix, then Ax comma x is real for every x in Rn. Even though the matrix A is complex as long as it is Hermitian, and even though the vectors x may be complex, A x comma x will always be real. Then we observe that if A and B are Hermitian, then A plus B is also Hermitian. Then if A is Hermitian, alpha is any complex numbers, then alpha A is Hermitian if and only if alpha is real. And finally, we had the property that if A and B are Hermitian, implies A B is also Hermitian if and only if A and B commute, that is A B equal to B. These are some simple properties of Hermitian matrices. Now, we mentioned that we are going to study Hermitian matrices in detail because they possess some nice eigen properties. So, we shall now begin our study of eigen properties of Hermitian matrices. We begin with a matrix A which is Hermitian, and so we now look at certain property. The first fundamental property that we are going to look at is the following. Suppose lambda is an eigenvalue of A. So, suppose we consider an eigenvalue of A. Now, lambda is an eigenvalue means there must be a corresponding eigenvector. So, this implies there exists a vector u not equal to theta n, u belonging to C n, such that A u equal to lambda u. That is what is meant by saying that lambda is an eigenvalue. This equation A u equal to lambda u, u is a non-trivial solution for this system. It always must exist if lambda has to be an eigenvalue. Now, that says lambda times u comma u can be written as lambda u comma u, because we know that when a complex number is a multiplier of a vector in an inner product in the first factor, then it can be pulled out without any change. So, lambda is a multiplier of u and it is in the first factor. So, it comes out as lambda outside. Now, lambda u is A u, because we are u is an eigenvector corresponding to the eigenvalue lambda. Now, we had the fundamental property of Hermitian matrices that A u u is always real, A x x is always real. We observed that if A is Hermitian, A x x is real. So, by property 3, that is we get this must be real. So, this is real. So, therefore, this implies lambda equal to A u u by u u. I can divide by u comma u because u is a non-zero vector and hence u u will be not 0, it will be a non-zero number. Now, if you look at the right hand side, the numerator is real, the denominator is real because u u is always real and greater than or equal to 0. The ratio of two real numbers is real and therefore, it says lambda is real. So, therefore, we have concluded that any eigenvalue of A must be real. So, the first fundamental property is that every eigenvalue of a Hermitian matrix must be real. Now, we observed last time that every real symmetric matrix can be thought of as a complex Hermitian matrix, and hence we get that every real version every eigenvalue of a real symmetric matrix must be real. So, there are lots of quantities that are associated with a Hermitian matrix that are real. We found that if A is a Hermitian matrix, all the diagonal entries must be real. We also found that if A is Hermitian, then Ax comma x is always real for all vectors x. Now, we have found that all the eigenvalues must also be real. So, every eigenvalue of a Hermitian matrix is real and every eigenvalue of a real symmetric matrix is also real. So, these are two, this is the first fundamental property, namely the eigenvalues being real is the fundamental property of Hermitian and real symmetric matrices. We now look at what it means in terms of eigenfunctions, eigenvectors. So, again let us look at a Hermitian matrix. A is Hermitian and suppose lambda and mu two distinct eigenvalues of A. Two distinct eigenvalues of A. Now, since lambda and mu are eigenvalues, there let u and v be corresponding eigenvectors. So, we have two distinct eigenvalues. What we mean is lambda and mu are different. There are two different eigenvalues we are considering and we are considering the corresponding eigenvectors. What does this mean? The fact that u and v are eigenvectors means u and v are non-zero, 1, and u is an eigenvector corresponding to lambda and v is an eigenvector corresponding to v. Now, notice that we have already shown that all the eigenvalues of a Hermitian matrix must be real and therefore, since lambda and mu are considered to be eigenvalues of the Hermitian matrix Hn, lambda and mu must be real. Okay. So, note by 1 lambda and mu are real. Now, therefore, we have these two distinct eigenvalues lambda and mu and we have the corresponding eigenvectors u and v. U and v are non-zero, Au is lambda u and Av is mu v. Now, this implies, let us look at lambda times u v. Again, this is the same as lambda u v because the lambda can be pulled out of the first factor. Now, it does not matter whether it is the first factor or in the second factor because it is real, it can be pulled out. So, it is lambda u v. Now, lambda u is A u from this and we know that for a Hermitian matrix Ax comma y is y comma Ax, the first fundamental property of Hermitian matrices. So, this is u A v since A is Hermitian. Now, u v A v is mu v by this property because v is the eigenvector corresponding to the eigenvalue mu. Now, mu has to be pulled out is a constant, it is a number, it has to be pulled out of the second factor, it will come out with a conjugate, but mu is real. So, conjugate does not matter. So, it will be just mu into u v since mu is real. So, therefore, lambda times u v is mu times u v and that says lambda minus mu times u v equal to 0. Now, lambda minus mu is a real number, u v is a complex number and the product is 0. the product of two complex numbers is 0 if and only if one of them is 0, but lambda minus mu cannot be 0 because lambda and mu are distinct, and therefore, that says u v equal to 0 since lambda is not equal to mu, because we have considered two distinct eigenvalues. Therefore, u is orthogonal to v. What this therefore says is, if you take two distinct eigenvalues lambda and mu and look at their corresponding eigenvectors, they must be orthogonal. They must be orthogonal. So, conclusion, this is the second fundamental property of the eigenvalues and eigenvectors of Hermitian matrix. So, eigenvectors corresponding to distinct eigenvalues, eigenvectors corresponding to distinct eigenvalues of a Hermitian matrix must be orthogonal to each other. So, they are nicely structured, the eigenvectors are nicely structured, they are orthogonal to each other. Now, the real version again is that eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal to each other, must be orthogonal to each other. Now, when I say orthogonal, in the real case we mean the real inner product, that is x comma y is x 1 y 1 plus x 2 y 2, there is no conjugation because everything is real. So, we have now these two fundamental properties, all the eigenvalues must be real and eigenvectors corresponding to distinct eigenvalues must be orthogonal to each other. Now, let us see what does this mean. So, therefore, let us look at a Hermitian matrix H n and let us say its characteristic polynomial is lambda minus lambda 1 power a 1, lambda minus lambda 2 power a 2, lambda minus lambda k power a k, where lambda 1, lambda k are the distinct eigenvalues of a 1, a 2, a k, their algebraic multiplicity. This is our usual notation. This is how we denote the characteristic polynomial and the distinct eigenvalues. Now, correspondingly we have the eigenspace, corresponding to eigenvalue lambda j. What is that? That is just the null space of A minus j I. Now, any vectors, let us consider j not equal to r, that is we are considering two different eigenvalues lambda j, lambda r. Okay. Suppose two indices j not equal to r, any vector in W j is either the 0 vector, or if it is not a 0 vector, it must be an eigenvector corresponding to lambda j. Similarly, any vector in W r is either the 0 vector or an eigenvector corresponding to lambda r. Now, if 0 vector is orthogonal to all the vectors. So, 0 vector is orthogonal to all the vectors in WR. If it is not 0, it is an eigenvector corresponding to lambda j, it will be orthogonal to 0 and it will also be orthogonal to all the eigenvectors corresponding to lambda r, because eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Hence, every vector in Wj is orthogonal to every vector in Wr if r is not equal to j. So, now let us see how this picture looks like. We have this W1, we have W2, all of them being orthogonal. The only vector that will be common to two orthogonal things will be the 0 vector. So, we have like that, and finally, Wk. So, we have W1, W2 etcetera, and we have Wk. They are so positioned that if you pick any one of them, every vector there is orthogonal to all the other vectors in every other piece. So, Wj vectors are orthogonal to every vector in Wr if r is not equal to j. So, what this means is Wr is contained in Wj perp and Wj is contained in Wr perp if r is not equal to j. Now, what does this lead us to? Now, suppose we find, let us look at Wj. The dimension of Wj is what we call as Gj, the geometric multiplicity of the eigenvalue lambda. Now, we shall at the moment not prove this theorem, we will simply say it can be shown that for any Hermitian matrix the algebraic multiplicity is equal to the geometric multiplicity for every eigenvalue, and hence every Hermitian matrix is diagonalizable. So, what does this amount to? Therefore, this says the dimension of Wj, which is Gj, the algebraic multiplicity, must be equal to Aj. Therefore, if I look at this piece Wj, this is the Wj, its dimension is Gj, therefore, Wj will have a basis. Let us call it as Bj. How many vectors it will contain? Since the dimension is Aj, it will contain Aj vectors. Let me call it as U11, Uj1, Uj2, Uj. The superscript j says that you are looking at the jth eigenspace, and the subscript gives the numbering, ordering of the basis vector. So, any basis of Wj will have Aj vectors, and now we can apply Gram-Schmidt to this to get an orthonormal basis for Wj. So, we can apply Gram-Schmidt to get an orthonormal basis. Let us now call it as Oj, as phi 1 1, I am sorry, it is phi j 1, because now we are looking at the jth space, phi j 1, phi j 2, and phi j Aj. So, we can get an orthonormal basis for Wj consisting of Aj vectors. We can do this for j equal to 1, j equal to 2 and j equal to k. Each one of these eigenspaces we can construct an orthonormal basis, and the number of vectors in this orthonormal basis will be exactly equal to the algebraic multiplicity of the eigenvalue. Now, if you put all these Oj's together, we have the union of these Oj's. Now, if you look at, let us write this down first, phi 1 1, this will be the one that correspond to the first eigenvalue. Then I will get those corresponding to the second eigenvalue and so on, and finally, those corresponding to the kth eigenvalue. So, this will consist of a 1 plus a 2 plus a k, which is n. So, this will consist of n vectors. If you look at the vectors here, they are all orthonormal, because that is an orthonormal for W 1, but across they are all orthogonal to each other, because eigenvectors corresponding to distinct eigenvalues must be orthogonal to each other, and therefore, this entire set is an orthonormal set, and since it contains n vectors, it is an orthonormal basis for Cn. So, therefore, we can construct an orthonormal basis consisting of only eigenvectors of A. Hence, we have a basis for Cn consisting of only eigenvectors of A. So, what is the consequence of this? We now define the matrix U, it is n by n, whose columns are these eigenvectors. What do I mean? We construct the matrix U, the first A 1 columns are the eigenvectors, orthonormal eigenvectors corresponding to the eigenvalue lambda 1. There are A 1 eigenvectors, we have applied Gram-Schmidt and we got A 1 orthonormal eigenvectors corresponding to the eigenvalue lambda 1, and that we put at the first A 1 columns. Then we put the eigenvectors corresponding to the second eigenvalue. The second eigenvalue multiplicity is A 2 and it has A 2 eigenvectors corresponding to it. These orthonormal eigenvectors are put at the next A 2 columns, and we proceed like this, and the last A k columns are the eigenvectors corresponding to the eigenvalue lambda k. So, this U matrix is made up of eigenvectors. It is made up of eigenvectors of A, it is made up of the orthonormal eigenvectors of A 1 of them which occupy the first A 1 columns are from the eigenvalue lambda 1, A 2 of them which occupy the next A 2 columns are the eigenvectors of lambda 2, and so on and so forth, and the last A k of them are the eigenvectors corresponding to lambda k. Now, since these eigenvectors form an orthonormal set, we see that by our very construction the columns of U form an orthonormal set. By our choice of these eigenvectors, we see that the columns of U form an orthonormal set. Now, why do the columns form an orthonormal set? Because these are all orthonormal basis for W 1, the next A 2 are orthonormal basis for W 2 and these are all orthonormal basis for W k, and these vectors and these vectors are orthonormal because when R is not equal to J, W j vectors are orthogonal to W r vectors. So, they form an orthonormal set. If the columns form an orthonormal set, we know that the matrix must be unitary. That implies U is a unitary matrix. That is what we saw at the beginning of the lecture. So, U is a unitary matrix, that is U star U is equal to identity. Right. So, therefore, starting from the eigenvectors of A, we have constructed a unitary matrix. What does this unitary matrix do to us? So, that is what we are going to look at. Now, what is A times U? Now, U is this matrix, A U will be multiplying each column by A, but when I multiply these first A 1 columns by A, because they are eigenvectors, they will be simply multiplied by number lambda 1. Similarly, the next A 2 columns will be multiplied by the number lambda 2 and so on. So, we will get the first column will be just lambda 1 phi 1 1 and then the A 1th column will be this. Then we will start with lambda 2 and we will have phi 2 1 lambda 2 phi 2 A 2 and this goes on and we get lambda k phi k 1 etcetera lambda k phi k A k. Because of the fact that every column is an eigenvector corresponding to some eigenvalue. So, it just gets multiplied by those vectors. So, therefore, we have U star A U is, we will start with phi 1 1 star and we end up with phi k A k star and this matrix here, and when we multiply we get phi 1 star phi 1 is 1 because of orthonormality and therefore, we will get lambda 1, but phi 1 star phi 2 will be 0, phi 1 star phi 3 will be 0 because of orthonormality, all the others will be 0. So, we get the diagonal matrix lambda 1 that occurs A 1 times, then lambda 2 occurs A 2 times, lambda 1 occurs A 1 times and then lambda k will occur A k times. This big diagonal matrix n by n we get A 1 plus A 2 plus A n is equal to this. We will simply write it as D, which is diagonal lambda 1 A 1 times, lambda 2 A 2 times and so on lambda k A k times. That diagonal matrix, we will simply denote it by D. So, we see that the matrix A is not only diagonalizable, but we have used a unitary matrix for diagonalization. Therefore, we say A is unitarily diagonalizable. Unitarily diagonalizable. So, thus every Hermitian matrix is unitarily diagonal. Therefore, A belongs to H n implies that is A is a Hermitian matrix means A is unitarily diagonalizable. That is, there exists a unitary matrix U such that U star A U equal to a diagonal matrix. The real version of this is the role of unitary is taken over by orthogonal matrix. So, A real symmetric implies A is orthogonally diagonalized. Is orthogonally diagonalizable. That is, there exists O belonging to Rn orthogonal matrix. Now, there is no star. So, O transpose A O is a diagonal matrix. So, real symmetric matrices are orthogonally diagonalizable and complex Hermitian matrices are unitarily diagonalizable. So, therefore, if A is Hn, we have U star A U is the diagonal matrix D as seen above. So, unitarily diagonalized. What does that say? If since U star is the inverse of U star U is identity. So, U star is invertible and its inverse is U. So, if we take the U star to the right hand side, it will go as U star inverse, which is U, and similarly U will go to the right hand side as U inverse, which is U star. So, this will be equal to U d U star, since U star inverse is U and U inverse is U star. So, this is a very nice representation of a Hermitian matrix. This says a Hermitian matrix can be decomposed as the product of three matrices. The two extreme matrices are unitary matrices and therefore, easily invertible, and the middle matrix is diagonalizable, is a diagonal matrix and hence can be treated easily. In other words, we have decomposed the matrix A into a product of three simple matrices. The middle one being diagonal is easy to handle, the remaining two being unitary are easily invertible. Okay. So, thus we have decomposed A belonging to Hn as the product U d U star of three simple matrices. The two extreme factors U and U star being unitary or easy to invert and the middle factor D being diagonal matrix is easy to analyze. So, there is a nice splitting of the matrix into simple factors. Okay, this is a factorization theorem or a product decomposition of a Hermitian matrix into simple matrices. A is equal to U d U star, U is Hermitian, D is diagonal, again U star, U is unitary, D is diagonal and U star is again unitary. So, this is a very simple decomposition of a Hermitian matrix. A more general version of this sort of decomposition is what we will see as the singular value decomposition. But for Hermitian matrices, we have a straightforward decomposition induced by the eigenvalues and eigenvectors, the eigenvectors constituting the unitary matrix U and the eigenvalues constituting the diagonal matrix D. you must notice here that in the decomposition we require u d. U star is known once u is known. U and d are the two required matters. D is known through its eigenvalues, because the diagonal entry D is the diagonal matrix whose entries are all these eigenvalues. The diagonal entries are all eigenvalues. You can notice that here all the entries along the diagonal are eigenvalues. Therefore, to construct this UDU, D requires only the eigenvalues, and the matrix U, you may recall, we have constructed using the eigenvectors. So, the two ingredients required to make this decomposition of the given into product of three simple matrices are precisely the eigenvalues and the eigenvectors, and that is why the eigenvalues and eigenvectors play an important role in analysis of a matrix. So, in the case of Hermitian matrices, you can conclude that thus for a Hermitian matrix, A, its eigenvalues and eigenvectors provide the product decomposition, we will call it. They provide the simple product decomposition A equal to U d U star, where to construct U we need the eigenvectors, orthonormal eigenvectors. So, we need the orthonormal eigenvectors of A, and to construct D we need the eigenvalues and their algebraic multiplicity, because I have to put diagonal lambda on A1 times, and therefore, I need the multiplicity, algebraic multiplicity A1, A2, AK, etc. Okay. So, a more general version of such a product decomposition is called the singular value decomposition, which is our ultimate goal. We will eventually get to that more general version of this singular value of this type of product decomposition. So, thus we have a nice decomposition of a matrix A into simple matrices, unitary, diagonal, unitary, unitary, diagonal, unitary. The diagonal entries are eigenvalues. Since A is Hermitian, all the eigenvalues are real. So, the diagonal part is a nice simple real diagonal matrix, and the other two are unitary. Anytime we can invert them by just flipping and conjugating them. So, that is the simple decomposition. We can also view this decomposition as a sum decomposition. We have viewed this whole thing as a product decomposition. We can also view this as a sum decomposition, which is essentially what is known as the spectral theorem for Hermitian matrices. Now, what we actually do for that is, we have the basis for Cn. So, we will in the next lecture we look at the details of these calculations. We look at what is known as a sum decomposition. We have the basis for Cn through eigenvectors. And this implies every vector in Cn can be expanded. Remember the so called Fourier expansion with respect to this orthonormal basis, with respect to this orthonormal basis. We analyze this expansion carefully to get the sum decomposition. And this is what we will look in the next lecture.